These are the notes for AP Calculus on the topic of differentiation and continuity. So continuity is where a function is continuous, but to be differentiable, that means the derivative has to exist at a point. So in order for a function to be differentiable, for the derivative to exist at a point, it first must be continuous. Or another way of saying that, if a function is not continuous, then it's not differentiable at that point either. It cannot be differentiable. So let's look at the intervals on which the function is continuous first, and we'll compare that to the intervals on which the function is differentiable, or combined derivative. So on this first one, we can see I have a vertical asymptote at -3, so it's not continuous at -3. So it'd be continuous on interval from -infinity to -3 with the parentheses, and then union, or U with, then from -3 all the way to infinity. And in this case, it's not differentiable at -3 either, because you can't draw a tangent line if it's not continuous there. You can't get the slope when there's no point of tangency. So it would be differentiable on the same intervals, from -infinity to -3, and from -3 to infinity. Let's look at the next one. Notice the next one, we've got a hole in the graph at x equals 2 right there. So if there's a hole there, it's not continuous. So we'd say it's continuous from -infinity to 2, and from 2 to infinity, everywhere but where the hole is. And same thing would be differentiable. Well, we can't draw a tangent on there because there's a hole. There's no point of tangency, so you can't get the slope or derivative there, so it's not differentiable at 2 either. So it'd be the exact same intervals. So far it's really not that interesting. The intervals which differentiable on are exactly the same word as continuous on. But now let's look at some cases where it can be different. So on this one, you can see it's continuous starting at -2 and with a bracket because it's got closed points, so -2 all the way to infinity. But at -2, if we try to draw a tangent line there, there's no way of knowing exactly where that tangent line is because the function just ends there. So because of that, whenever a function just ends at a point like that and stops, it's not going to be differentiable at that end point. So it would be differentiable, it would be starting at -2, but with a parentheses, so we're not including it, and then to infinity. So that's one case where it's slightly different, or it is continuous but not differentiable. But let's look at the major cases now where a function is continuous but not differentiable. So on this one, you can see it's continuous everywhere. It's just like an absolute value graph. It's continuous from -infinity to infinity. And if you take a look, there's one place that's not differentiable, and that's right here. Because right there, how would you know where the tangent line goes, right? There's no way to tell exactly where that goes. So it's differentiable on -infinity to 0, and then 0 to infinity. And what's happening there, this is called a corner. So in the corner, we have an abrupt change in slope. So you can see the slope, -1, -1, -1 second, then all of a sudden it's positive. So there's not a smooth transition like on a normal curve. So whenever you have an abrupt change, a corner like that, it's not differentiable at that corner. Then let's look at the next one. It's kind of a similar thing on this one. Again, you can see it's continuous everywhere, so from -infinity to infinity. But again, we've got this abrupt change in the slope right here. This one, though, has a different name. This is called a cusp. So it's still, you can't draw a tangent line there because it's an abrupt change. It suddenly goes like that. It's not a smooth transition there. We have an abrupt change in slope. The reason why it has a different name is if you were to zoom in on that region, like using a graphing calculator, what you'd find is on the left, it's actually getting steeper and steeper. The slope is actually approaching negative infinity, and on the right, it's approaching positive infinity. So you can't get more abrupt than that, going from a negative infinity slope to a positive infinity slope. That's why it has a different name on the cusp. So it'd be differentiable everywhere but that cusp. So from negative infinity to 3, and then from 3 to infinity. The next one, again, you can see it's continuous everywhere, from negative infinity to infinity. There's no corner or cusp. It's a nice smooth curve, so there's no abrupt change in slope there. However, if you take a look right at negative 2, you can see the tangent line there. You could draw it, unlike the other two. However, it would be a vertical tangent line. And just think about any vertical linear equation, like in this case the tangent line, the slope is undefined. And if the slope is undefined, remember, derivative is the calculus word for slope. That means the derivative would also be undefined. So it's differentiable everywhere but where that vertical tangent line is. So from negative infinity to negative 2, and from negative 2 to infinity. Now let's take a look at one where you're given the graph. It says below is the graph of f of x. F of x has a vertical tangent line at x equals negative 3. Well, that's just telling you right where it is. So you don't have to guess about where it is or if it's exactly vertical. And a horizontal tangent line at x equals negative 7. Well, the horizontal tangent line, the derivative exists there because the slope is just 0 horizontal. It's only the vertical tangent lines where the derivative does not exist. So it says determine the x values where the function is continuous but not differentiable. And then we're going to justify our answer. So the first place, we've got a vertical tangent line right there, so we can say, here the function is f, so we can say f is continuous but not differentiable. At x equals negative 3. And your justification is since, well, the way we specify that, rather than just saying there's a vertical tangent line, that already told us that, since when we have a vertical tangent line, the derivative is undefined. The way we say that is since f prime, it's not f prime of x though, because we don't want to say it's undefined everywhere, just at negative 3. So we say f prime of negative 3, that's the derivative or slope at negative 3, where we have a vertical tangent line, that is what's undefined. And there's one other place where it's continuous but not differentiable, and that's right here. You can see we've got a corner. There's an abrupt change in the slope. So we can say f is continuous, but not differentiable. At x equals 1. Your justification, though, would be different. This is how you justify either a corner or you justify a cusp in the same way. And that's since, similar to how you justify something's not continuous when the left and right hand limits are not equal. But in this case, the left and right hand limits of the original function are equal, because they do meet up. So what's not equal is the left and right hand derivatives, or slopes. We'd say the limit as x approaches 1 from the left, not of f of x, but of f prime of x. That refers to what the slope is approaching from the left, does not equal the limit as x approaches 1 from the right of f prime of x. That's what the slope is approaching from the right. Now let's take a look at a piecewise function. It says let g be a function defined by this right here. So the first part, a little review, says is g continuous at x equals 4. So 4 is our breakpoint. So to see if it's continuous, well, we just find the left and right hand limits of the original function. So do the limit as x approaches 4 from the left of g of x. From the left, we'd use the top piece. That's where x is less than 4. So I'd be plugging 4 there. 4 squared minus 4. That's 16 minus 4 gives you 12. From the left, the function's approaching 12. And let's compare that to the limit as x approaches 4 from the right of g of x. So from the right, we use the bottom piece. So it'd be 5 times 4 minus 8. That's 20 minus 8, which is also 12. So since those are the same, that means the general limit exists and it's 12, and it's also continuous. So we can say g is continuous at x equals 4. Or I guess we could have just said yes, it's a yes or no question. And then your explanation would be since the limit as x approaches 4 from the left of g of x equals the limit as x approaches 4 from the right of g of x. Now let's look at beyond that. Let's see how can we determine if g is differentiable at form. So this is the first time we'll actually take the derivative of a piecewise function. You just take the derivative of each piece separately. So g prime of x, the derivative of the top piece would be 2x minus 1. That applies if x is less than 4. And the derivative of the bottom piece would be 5. That applies if x is greater than 4. The only thing I'm going to do is drop off the or equal to on the second piece because we don't yet know if the derivative exists at 4. If it does, we'll add that equal to back in. But right now, it doesn't. Or we don't know if it does. So we're going to leave it off for now. Otherwise, if you had it there, it would mean the derivative at 4 is 5, which could be, but we don't know that yet. All right. So now we do a similar thing that we did to its continuous. To make sure it's differentiable, what we have to see is whether these left and right hand limits, like here they were not equal, we use the graph. But we want to use the equation this time to determine if we've got a corner there or if it's a smooth transition. So now we'll find the limit as x approaches 4 from the left of g prime of x. Plug in 4 into the top piece, that'd be 2 times 4 minus 1. Gives you 8 minus 4, sorry, 8 minus 1 is 7. And then a limit as x approaches 4 from the right of g prime of x. Well, from the right there's nothing to plug into, it's just 5 because this is a linear equation, the slope is always 5. You get 5. So this time these are not the same. So that means that we have a corner. Not the same. So that means it's not differential. So we can say, answer our question, is g differentiable at x equals 4? Say no. And our explanation would be since the limit as x approaches 4 from the left of g prime of x does not equal the limit as x approaches 4 from the right of g prime of x. And if they were equal, that would mean it's a smooth transition. They're close, 5 and 7, they'd be exactly the same. If they were, then you'd say, if they're both 7 or both 5, you'd say yes, and then you just justify it by saying that these left and right limits of the derivative are equal. So what this looks like graphically, to give you kind of a visual of this, we've got 4, and we know they meet up at 12. So they meet there at 12, they approach them both the left and the right. But from the left, we can see it's a parabola. From the left, the slope's approaching 7. Pretty steep there. And from the right, it's a linear equation with a slope of 5. Okay. So, exaggerate a little bit, but you can see because those are not the same, we do have a corner there. Even if it's not as drastic as some corners, you still have a corner because the left and right hand limits of the derivative were not equal. Now let's take a look at another piecewise function. It says suppose f is defined by this piecewise function, where k and m are constants. Okay? So that just means they're numbers like a 2 or a half or -3. So as we go through the problem, we have to treat them as constants. And it says if f is differentiable at x equals 2, what are the values of k and m? So first we have to make sure it's continuous at x equals 2. Because it can't be differentiable if it's not continuous first. So that's where we use the original function and set the limit as x approaches 2 from the left of f of x equal to the limit as x approaches 2 from the right of f of x. So from the left, you'd use the top piece, this is the left of 2, so that'd be k, we're just plugging in 2 for x, not for k, all right, times the square root of 2 plus 7 equals the limit as x approaches 2 from the right, you'd use the bottom piece, that'd be k times 2 squared plus n times 2 plus 15. And let's go ahead and simplify this. That's the square root of 9, which is 3 times k, so 3k equals 2 squared gives you 4, so that's 4k. 2 times m is 2m, and then plus 15. And you can subtract the 3k over and subtract the 15 over to make it simpler, so you've got negative 15 equals, subtract the 3k from 4k, that gives you k, and then plus 2. But that alone is not enough to solve for k and m. It's only one equation and 2 unknowns. So we get our other equation by making sure it's also not just continuous, but differentiable. So just like we did over here, we need to find the derivative of the piecewise function. By finding the derivative of each piece, the only thing I'm going to do is rewrite this top piece here. This is in radical form. That's the same as k x plus 7 to the 1/2 power. So now let's find f prime of x for the derivative of the top piece using the chain rule, because we have a function inside. Take 1/2 times the constant out front, so do 1/2 k times, function inside stays the same, x plus 7 to the negative 1/2. And then times the derivative of the inside, well, the derivative of x plus 7, though, is just 1. And that applies for, again, I'm just going to drop off the equal to signs, because at this endpoint, remember when a function just ends there, it's not differentiable, and we don't yet know at the breakpoint, too, if it's going to be equal or not. Actually, we're going to make it equal in this case, so we can leave it, because we're going to force these to be equal to make sure it's differentiable. And then for the derivative of the second piece, it's a little bit easier. K is a constant, so the 2 just comes out in front, so it's 2kx plus the derivative of mx. So the derivative of 2x would be 2, the derivative of mx is just m. The derivative of 15 is a constant, that's just 0. That applies for 2 is less than x, less than 6. Again, and I drop off the equal to sign. Since the function just ends at 6, it's not going to be differentiable there. Now let's make sure, not only is f continuous, let's make sure f is differentiable at x equals 2. So to make sure it's differentiable, now we set the left and right hand derivatives equal to 2. So the limit as x approaches 2 from the left of f prime of x has to equal the limit as x approaches 2 from the right of f prime of x. So x approaches 2 from the left, we'll use the top piece, and as we go, I'm going to put this back in radical form. So for fraction, we have k on the numerator, 2 on the denominator still, and this is going to move to the denominator as a square root, and we'll plug in 2 for x, and 2 plus 7 equals, substituting 2 for x on the other one, 2 from the right, that's going to be 2 k times x is 2 plus n. And we simplify this, see that's square root of 9, which is 3 times 2 is 6, so we get k over 6 equals 2 times 2, that gives you 4k plus m. And then if you want to wipe out the fraction, you can multiply this all by 6. So you got 6's cancel there, just k equals 24k plus 6m. And then you can subtract the 24k over or subtract the k over either way. Probably easier if we subtract the k over there. So if we subtract the k over, we get 0 equals 23k plus 6m. So now we have two equations, two variables, so we can use either substitution or elimination. We'll solve this. In this case, substitution wouldn't be too bad since it's not too hard to get k by itself here. It's isolated and substituted. But since these are already kind of set up for elimination, let's go ahead and do that. So to use elimination, we just multiply this one to get the m's to cancel. It's probably easier than the k's. Multiply this one by -3 to make it a -6m. So that'd be positive 45 equals -3k minus 6m. And if we bring this one over, that's 0 equals 23k plus 6m. Add them together, 45 and 0 gives you 45. 23k minus 3k, that's 20k. The m's eliminate, which is what I wanted. And then divide by 20. So k would equal, reduce that, you can divide those both by 5, so that would be 9 over 4. So now we know what k is, 9/4. And then to find m, we can substitute in any of these. So I'm just going to substitute in right here. So for that one, so we'll have 15, -15 equals k, which was just figured out as 9/4. And then plus 2m. So again, if you don't want to have to deal with the fractions, what you can do is just multiply it all by 4. So 4 times -15 is -60 equals 4 times 9/4, the 4's cancel, gives you 9. 4 times 2m is 8m. And subtract the 9, which is -69 equals 8m. Divide by 8, we get m equals -69 over 8. So those are the constants. If we were to substitute in for k and m back into this equation here, it would make it a nice, not only continuous at 2 at the breakpoint, also make it a nice smooth transition at 2, because the slopes from the left and the right are also equal derivatives. Finally, let's take a look at one similar to one we did before, but the way they ask you to justify it is a little bit different. So it says a continuous function f is defined on the closed interval. The graph of f consists of the line segment and a curve as shown in the figure above. So it says, is f differentiable at x equals -4? Use the definition of the derivative with one-sided limits to justify your answer. So at x equals -4, we've got a horizontal tangent line. So the derivative there, f prime of -4, would just be 0. The slope is 0. So it is differentiable. So answer our question by saying yes. But the way you have to justify it, normally you'd say since the limit as x approaches -4 from the left of f prime of x equals the limit as x approaches -4 from the right of f prime of x. However, it says specifically you have to use the definition of the derivative with one-sided limits to justify your answer. So remember the definition of the derivative. I'll write it up here to refresh your memory. Remember, this is what we used to find the derivative before we learned all the shortcuts. So f prime of x, remember, equals the limit as h approaches 0, f of x plus h minus f of x all over h. So what we have to do here, this is the derivative at any value, is use the left and right hand limits of that in that form. So it would be the limit as h approaches 0 from the left, but it's not the general derivative here, it's the derivative specifically at -4. So since x is -4, we're going to substitute that in, put x there and right there. So it's going to be the limit as h approaches 0, f of -4 plus h minus f of -4 all over h. And then what that doesn't equal is the limit, the right hand limit. So one-sided limits, that means your left and right hand limits, as h approaches 0 from the right, of f of, again, -4 plus h minus f of -4 all over h. And then it says that f differentiable at x equals -2. So at x equals -2, we can see we've got a corner there. So there, the derivative would not exist, so it is not differentiable. So the answer here would be no. Oops, I forgot to add the word since here. So we've added this word since. Again, it says use the definition of the derivative with one-sided limits to justify our answer. So we can do it in the same fashion. Oops, on this one I apologize. This one is, they are equal. They're both approaching 0 from both sides. So that was equal to. But this one, they're not equal. From the left and the right, you can see there's an abrupt change in the slope. So this time, be the limit as h approaches 0 from the left. F of this time x equals -2 instead of -4. So f of -2 plus h minus f of -2 all over h. This time it does not equal. It's from the left and the right. The slopes are approaching different things. The limit as h approaches 0 from the right of f of -2 plus h minus f of -2 all over h. That concludes the notes for AB Calculus on the topics of differentiation and continuity.